The integral test is an excellent test for determining convergence of series, but sometimes it's a little bit cumbersome to use it when the series is too complicated, and we can often look at a series such as this one and determine its convergence much more easily by this so-called limit comparison test. Notice that if we try to use the integral test for this, the corresponding integral will be 1 to infinity of 1 over x squared minus x, and we'd have to use the partial fractions technique to do that, which would be sort of time-consuming. It turns out that this integral here is actually very similar to the integral 1 over n squared, which we know converges, and so we're going to be able to use the fact that we know 1 over n squared converges and behaves close enough to the series here to prove its convergence. So let's see how to do that on the next blackboard. So if we take the limit as n goes to infinity of the terms of this series here, which are 1 over n squared minus n, and compare them to the terms of the series that we know converges 1 over n squared, let's see what we get. So we get, by flipping and multiplying limit as n goes to infinity, n squared over n squared minus n, which is the same as the limit as n goes to infinity. We'll divide everything through by n squared, so n squared over n squared over n squared minus n over n squared, and we either have the limits or the values of these. This is 1, this is 1, and this goes to 0 as n goes to infinity. So we see that the limit, the comparison of the limit of the terms of these series is 1, and that is sufficient to allow us to say that because this series here converges, therefore this series right here converges. So more formally, here's what the limit comparison test, or here's how we state the limit comparison test. So here's the limit comparison test as it's formally stated on page 196 of the text. So we just use this version of the limit comparison test. We found a series that converges summation 1 over n squared, and we used it to show that the series that we wanted to look at right here, 1 over n squared minus 1, converged. We could also use the limit comparison test to show divergence. So let's take a look at how to do that on the next blackboard. Before we do that, let's make special note that when we compare these limits, that limit that we get cannot be 0 or infinity. Notice that when we got our limit here in this first example, it was 1. So let's do this next example here, example 3 on page 196 with this infinite series. So when we look at this series, we see that we have a power in the top of 1 and the first power, and in the bottom we have a power of 5/4. So a good series to compare it to would be the difference of those powers, which is n 1 over n to the 1/4, which we know diverges. So let's see if we can get the comparison of limits to be a number other than 0 or plus or minus infinity. Should be pretty clear that that is not so difficult to see before we actually formally do the limit. So we're taking the terms of our given series and dividing it by the terms of one of the series. So we're inverting and multiplying. That gives a numerator of what, 3n to the 5/4 plus 2n to the 1/4 that we're dividing by n to the 5/4. So let's continue on the next blackboard. And so it should be clear that that when we use the technique for determining this limit of dividing through by the highest, or dividing through numerator and denominator by the highest power of n in the denominator, we get that this term is 3, that this other term in the numerator goes to 0, this term in the denominator is 1, and so the comparison of these limits leads to 3, not 0, not plus or minus infinity, and therefore, since this series diverges, the series that we were looking at diverges. The reason, by the way, that these limits cannot be 0 or infinity, if they are 0 or infinity, then the series we are comparing it to is either too small compared to the series in question or too large to make the comparison valid. So that's why we have this restriction right here on the limit, so that we know the comparison is valid. So there's another example in your text, example 2 on page 196 that I want you to look at prior to coming to class. There's an example where the limit, the comparison of limits leads to 1/5, so it's a valid comparison, but the series we're comparing to converges in that case because its power is 11/5 larger than 1, or 6/5, excuse me, and that shows convergence. So this concludes this video on section 9.2.